show some of the very interesting videos. So my name is Zachary Shaffer, and I'm a myrmecologist. I'm an ant researcher from Arizona State University, and I'm here to talk to you about my project called the Foundress' Dilemma: Group Selection for Cooperation Among Queens of the Harvester Ant, Pogonomyrmex californicus. So ants actually have variability in the founding strategy. When it comes time for a colony to be started, a queen actually flies out of her mother nest, and not everyone knows that, of course, ants have wings. They're kind of wasps. And so the young queen will leave her nest and fly off, and then she has to find a spot to dig into the ground and start her own colony. But what's not often known by many people, aside from myrmecologists, is that in some cases you can actually get cooperation among unrelated queens to start new nests. So here I have this picture, and you see there's kind of a goat-alone individual at the top, the queen, and then down at the bottom, those are all queen ants that are banding together. So there's actually variability in this, and usually this varies by species and by population. So some species always go it alone. Sometimes some species the queens cooperate. So it's variable. So the species that we study is Pogonomyrmex californicus. This is the ant that, if any of you ever had, you can raise your hand, Uncle Milton's ant farm, where you got this for your kids. They send you the workers from this kind of species, and of course the workers gradually die. The onion system, like ant farms, teach children about futility, toil, death. But the real way, if you really want to have a real ant farm, what you want to do is you want to collect the queens, because if you have a queen, the colony can survive as long as the queen exists, and she'll lay many eggs on many workers. And so you can see on the picture, there's some ant farms, and that's the ant right there. And so we found, as previous researchers have found, that there is this variation in colony funding strategy in a very close geological area. So in Pine Valley, California, so in San Diego County, there are two populations that are close to each other. One population is predominantly haplomatronic, which means the queens kind of go it alone, and the other population is predominantly pleiomatronic, which means the queens tend to cooperate. So that's a pretty interesting behavioral polymorphism that researchers at Arizona State University have been pursuing for many years. Unfortunately, I can't show the videos here. But this photograph can show you, so basically the consequences of the violence. So in many cases, the queens will band together and live quite peaceably, but when violence does erupt, it's a life and death matter. And you can see here that this queen it's like some kind of Game of Thrones, Dothraki thing. She has the head of another ant around her waist. It's like something, like the ultimate kind of barbarian ornament. So these ants are going to fight to the death. And you can see that this queen who's dead, that she had to sever the head of her opponent or she would die. And apparently she expired after the battle was finished. So this is a matter of life and death, these struggles. Unfortunately, couldn't show these video clips. If I have time, I'll show you a few clips on my zip drive. So our method was that we go to California, Pine Valley, at the height of the queen flying season. Of course, the queens fly at certain times of the year. It has to be tuned to the environment, rainfall. Usually it's around the time of the summer rains. And we collected thousands of queens, and we set them up in these ant farms at Arizona State University. And so this is what our experimental design was like typically. And there are other aspects to it as well, but just for simplicity, I'll break it down. We wanted to see what was the effect of having these kind of good queens and bad queens. So we called them, cooperators and defectors. So we were very much influenced by these ideas that are in game theory. And so we assembled groups of 6, and you can see we would put individuals from purely the pleiomatronic population in one group, and the other group we'd have mostly individuals from the pleiomatronic with one individual from the haplomatronic population. And we wanted to see what were the effects on the fitness, basically survival and productivity. And we found there was no effect. It was very odd, because this experimental design, there was nothing. It was like the ants all seemed to die, but we saw these individual cases where there was something clearly going on. And so what we did was we rethought our analysis. And so it turns out that aggression is very important in determining the survival of these queens. And actually, if you look here, we calculated that this is an ant aggression index, that in the haplomatronic population, there is a lot more aggression. Let me see if this is a laser. Let's see, it's not working. Oh, there we go. The haplomatronic population tends to have a much higher rate of aggression per ant day. But then there's also actually in the pleiomatronic population, surprisingly, there's also aggression there. So in general, the haplomatronic population is more aggressive, but in some cases we found there were individuals just as aggressive in the Paleometrotic population. So what we did then was we reanalyzed things. Instead of analyzing the data based upon population of origin, we just took them at face value based on their behavior. And what we found was this. So we see that in the groups, this is a survival analysis, so we see that in groups where we had aggression, the aggressive queens were the survivors. And so they basically killed everybody else. It was like the Godfather Part 2. They would just want to try and take out their opponents. And so the aggressive queens were sort of the winners in their group, if you will. And these are all of the peaceful kind of chumps that were, whose heads and abdomens we found severed every day. And in fact, if you look here, that in 27 groups where we had documented aggression, in 15 of those, the most aggressive ant was the last ant standing. So it was like a battle to the death. So she killed all 5 of her nestmates in many cases. Now, but when we analyze the survival based upon not the individual, but the survival of groups, so basically compared groups that had no aggression with groups with aggression. This is individual survival. Individuals in groups with no aggression really survived much longer, had a much higher chance of survival than groups where aggression occurred. And furthermore, if we compared, so that was the survival of individual ants. If we compared the survival of whole groups, so like think of the whole group as kind of a functional unit, the groups that had no aggression, almost 80% of them were still alive and kicking, producing eggs and even small workers at day 60 of the experiment. Groups with aggression died out really quite quickly. So all this, what does it all mean? Like, how can we draw larger kind of conclusions from this and kind of give you context? It's always great in evolution when you take things back to Charles Darwin. And so back, when Charles Darwin was writing The Origin of Species, one of the things that gave him a really hard time was the cooperation of worker bees and worker ants with the queen. So there's why it's all this brutal survival, fight for survival, survival of the fittest. Why would you sacrifice your own personal reproduction for your queen? And he said it was the one special difficulty which at first appeared to me insuperable and actually fatal to my theory. And Darwin, in his intuitive way, actually did come upon a solution. And the idea was that he realized that, this is the mystery again, he realized that if you look at the individual, is that he basically said the neuter workers make sense if the individual under selection is not the solitary ant, but the entire colony. So what Darwin realized was that it wasn't just the individual ant that was being selected, it was the family unit or the entire colony group. So in this moment, you kind of have the seeds of some very important ideas in social evolution. You could argue that that is maybe one of the early insights that led to inclusive fitness theory, which we all know is very important in explaining cooperation in the natural world, but also it was the seed of the thought that led to the idea of group selection or multi-level selection. And so the ant foundress case actually very closely resembles the haystack thought experiment of John Maynard Smith, in which you imagine, so you have all these groups, and if you have in this thought experiment, there are these mice-like creatures. So these red ones are the aggressors, and the blue ones are cooperators. In a given group, the red one is going to win in Maynard Smith's thought experiment. It's going to basically have an advantage over its blue competitor. But the groups that are composed purely of cooperators will have some advantage of reproductive or some other advantage over groups that have this non-cooperators. And so really the case that we have made is that in P. californicus, that we have a natural analog of the famous chicken experiment by Muir, group selection. This is, everybody who's interested in group selection, this is our favorite experiment with these chickens. It's worth taking a moment to describe. So what Muir did was he was a chicken breeder, and there was a real problem in the chicken industry in that the chickens, they would select the chickens that were the most fecund. Like you pick we want the chickens that lay the most eggs, right? So they pick these chickens, and but those chickens, there's chickens of a dominance hierarchy, as we all know. Those chickens were vicious, and so basically they would have these groups of hens all comprised of alpha females, and they just peck the hell out of each other. So in the chicken industry, you have a terrible problem with like injuries from beaks. They have to do beak removal surgery. They have to give antibiotics to deal with the injuries. So what Muir did was he said, what if we, instead of picking the most fecund individual, who's also probably the most aggressive, what if we pick the most fecund groups? And And so for multiple generations, he did that. He'd use a group of related hens, and he picked the groups that had the most eggs. When he was done, he had these chickens that were the most just chill chickens, just copacetic, just you can pack them in like sardines, they're just chill, you know. And so these chickens are super chill, and they laid eggs like gangbusters. So it's actually a rare example of a scientific experiment that was not only fascinating but also economically valuable. These chickens were millions of dollars, of course. And so what we're claiming is that our ants essentially are a natural analog. And I really enjoyed Vincent's talk where he talked about how you essentially could have kind of population-specific effects of social interaction. So it seemed like that with the beetles, you had higher densities that led to different effects on selection of horn length. And so in this case, it turns out there's something very similar, we think, going on with the queens, that basically it's a, I don't have time to go into it, but it's a population-specific and density-dependent situation where, essentially, when the queens are packed together in dense aggregations, that's where you have the intense selection for cooperation. So what we're claiming is that this is a natural analog to Muir's experiment with the chickens. And really the take-home is that the idea is that when natural selection is acting upon whole groups, we can imagine that the individuals that are good team players are going to become more common as their groups outcompete the groups that have more selfish actors. And so that's the idea of group selection. And also, far from being rare, this idea of group selection or multi-level selection, it's really, and I've been the first one to say I love inclusive fitness theory. I think it's so valuable in understanding cooperation. But the multi-level selection is an equally important and kind of related concept that we can really learn a lot from. And it's part of this glue that holds life together, all of the different hierarchical levels, I think. And so with that, I hope you guys will check out our paper, published a little less than a year ago. And I want to thank these folks, especially Stephen Pratt and Jennifer Fewell, who are my co-advisors in this. You might say I was sort of like their worker ant. And my excellent colleagues, Takao Sasaki, who was one of our modelers, and Marco Janssen. And then Brian Haney, I got a chance to talk about his ecological detective work. Brian Haney kind of put it all together out in the field, studying these nest densities. And so I thank you for your attention. Thank you. Yes, sir.
Do you see, so in about little less than half, you had not the most aggressive ant as the last one standing?
Yeah, sometimes, yeah. So it was costly. It was like being aggressive was a costly strategy.
So my question is do you see any policing going on? So, right, if you've got an aggressive ant, everybody gangs up and kills that aggressive ant. Now you've got a non-aggressive group. So do you see any type of aggressive or policing behavior?
That's a good question. I didn't see that. There was a scene that usually the peace plants would fight back or try to avoid the most aggressive ant. In one case, there was an aggressive ant and it led to a complete societal breakdown. Like I saw one ant attacking another on one day, and the next day they all were at each other's throats. Like I'm not sure if they were able to keep track of who was biting whom, but it seemed like the social contract was violated, and then they all were dead. So again, there wasn't any policing in this sense. And it's important to emphasize that we're not explaining the evolution of eusociality. This is sort of like icing built on top of the cake of eusociality. This is a more derived form of cooperation. So we're not making any claims to explain eusociality. So, yes.
I have two questions. The first is...
It seems I'm out of time, so I meant to see, is there a next speaker here? Yes.